Hi, I am Akhilesh Soni. I am a PhD student in the Department of Industrial and Systems Engineering at University of Wisconsin-Madison. I am jointly advised by Professor Lindroth and Professor Lutke. In this work, I'll be presenting our work on mixed integer linear programming for scheduling operations in an unconventional oil field development. So here you can see a typical layout of a shale oil field. So the entire field is divided into few pads. Each pad is a piece of land which consists of 2 to 6 wells. So the set of operations on a pad is drilling followed by fracturing, and then finally we can produce from a pad. And once we start producing from a pad, production declines over time exponentially. So we did like a piecewise linear approximation for the curve. And then another problem in this scenario is that there are interaction effects. So if you are fracturing a well, if you are fracturing a pad, then you cannot produce or drill in the neighboring pads. So our goal here is to determine how to optimally schedule the drilling and fracturing operations for each pad, and we have to maximize the net present value of the project. And it is important to highlight here that we are focusing on solving large scale instances with like greater than 100 pads and 10 to 30 years of horizon. So to give you a better insight into the problem, here I am showing a illustrative example. So the field here consists of 20 pads, and which is assumed that it is like spread out in a rectangular grid. So if you see observe P11, so P4, P10, P18 and P12 are sort of the neighboring pads here. So if you are fracturing on P12, as you can see here, the green rectangle is showing that it is getting fractured, P12. So you can see that P11 had to be shut down when we were fracturing P12, and this is what interaction effects like does to the schedule. So these kind of conflicts are realized, you can realize them like they are spread out throughout the entire schedule. And this Gantt chart or the schedule for this was generated using a baseline scheduling algorithm. So baseline scheduling algorithm is sort of a greedy algorithm where we prioritize the pad with a higher production expected production volume to be operated first. So to get into the mathematical formulation next, I introduce some decision variables first. So first set of variables is the variables which keep track of when did the drilling or fracturing started on a pad. So X is for drilling and Y is for fracturing, which take the value of 1 if drilling started on pad P in period T, and similarly for Y variables for fracturing. Next I have a variable WPT. So WPT is keeping track of whether the pad was producing in period T or not. So it's like a binary variable again. And then I have a continuous variable which keeps track of how much amount of oil was actually produced from pad P in period T. And finally, our objective here is to maximize our NPV. So here you can see that my NPV is sort of into two different parts. So the first one is like the revenue generated in period T. So the first term here is essentially your price of oil into your volume produced. So this gives revenue, and then the next two terms are the cost associated. So the first term is for drilling cost, and the second term is for the fracturing cost associated. And like the entire revenue is time discounted to current day. But we also need to consider out of planning horizon revenue, which is the second term in this case. Because it might occur that because these projects take like a little while, like decades, to break even. So it's important that we need to consider out of planning horizon revenue, otherwise the model doesn't think that it is profitable to operate any pad. So beta PT here takes care of whatever the revenue you might earn after our optimization horizon revenue based on the production curve for each pad. So next, getting into constraints. So our first constraints are the set of capacity constraint, because we have a fixed number of drilling and fracturing crews, which are ND and NF here. So the number of parallel operations for drilling or fracturing cannot exceed their respective crews. Then we also have vicinity constraints, which I just discussed earlier, that you cannot drill or produce if you are fracturing in a neighborhood. And finally, the most important constraints here are the oil production constraints. So alpha PT minus K here is sort of keeping track of your production curve. So alpha PT is simply a production curve, and this constraint help us to impose that production curve as soon as the pad is fractured. And there is another thing which we need to take care is that, like, even after like we impose the curve on these V variables, it might still need to be shut down because there was some interaction effect going on. So we introduce another constraint with the upper bound on VPT essentially, and if WPT is 1 then it doesn't say anything, but if WPT is 0 then it forces the production to be 0, and that is exactly what we wanted. So this was the first formulation which we proposed, so MILP1. So next, to improve our bounds on the oil production constraint, we introduced this extended formulation where we have slightly higher number of variables, but which help us to give like obtain better LP relaxation. So I introduced a new variable here, ZPKT, which essentially says that it's a binary variable and it takes a value of 1 if pad P, which was fracturing in period K, is producing in period T. And then we have to introduce some new logical constraints to relate to the previous decision variables. So the first constraint here typically says that if WPT is 0 for a period T, then all the ZPKT variables for K less than T minus tau of P are 0. And if WPT is 1, then it simply states the redundant constraint. So the second constraint is essentially saying that if your pad wasn't being fractured in period K, then there is no way you would be producing in that entire set. So the entire set turns out to be 0. And the last constraint is saying that your VPT is equal to your production curve and then multiplied by ZPKT. So this takes care of both the things simultaneously. Like it takes care of imposing the production curve along with switching on, like taking care of whether the pad was actually producing or not. So because our objective is to maximize our objective is maximization, and it increases by increasing VPT. So ZPKT is forced to be 1 when these two constraints allow it to be. And as I discussed, this is a larger formulation, but it gives us better LP relaxations. So in this slide, I'm showing some results comparison for our our formulations. So I'm considering 4 scenarios here. So the first two have relatively higher number of periods, and the second two have like relatively lower number of periods. In all 4, however, you can see that the extended formulation does much better when it comes to LP relaxation gap. And even the number of nodes explored are fewer in our extended formulation, saying that okay, we did actually get a better formulation. However, the computational time is actually better in the first 2 cases for our original formulation, but in the second 2 cases it's much better for our extended formulation. So we concluded from here that okay, extended formulation does give us better results, but only for a fewer number of time periods. So next, I want to introduce our rolling horizon framework. As I discussed at the starting, because our focus was on solving very large scale instances, and it's not possible to solve large scale instances in a single, like the problem gets intractable. So we propose this rolling horizon heuristic where you roll on a daily basis, and you keep solving the model as and when you have a crew available, like crew which is not assigned to any pad right now. So, and the model is solved slightly on a coarser scale, like maybe weekly or bi-weekly or monthly, but we roll on a daily basis. And instead of looking till end of horizon, we only look for maybe 30 to 40% of the horizon, so that the model is tractable. And as you keep moving forward, the rolling window keeps getting pushed ahead. So here I want to compare our rolling horizon approach with our baseline approach. So here I am considering 4 cases with pads varying from 80 to 110 and periods varying from 100 to 180. So in all 4 cases, you can see that our rolling horizon improvement was like 4.5% to 6.5%, which is quite significant when you see the scale of the NPV, which is like 30 to 40 billion dollars. And in the graph on the left, I'm showing that when like the periodic prediction for the rolling versus baseline, you can see that periodic production was like way earlier for our rolling horizon compared to our baseline heuristic. And in the graph on right, you can see that even the cumulative oil production for rolling horizon was way above, like was above than our baseline heuristic. So we can see that okay, our rolling horizon actually is a good approach. So just to conclude at the end, in this work we presented a MILP based rolling horizon algorithm to solve this scheduling problem in an unconventional oil field development. We studied 2 different formulations, MILP1 and extended formulation. And in the rolling horizon framework, we actually got pretty good results which varied from 4 to 6%. So if you have any questions, you can email them to me at sony6@wix.edu. Thank you.